Okay. We have 20 minutes. Let's see what we can finish today. We'll finish vitamins and start minerals for sure. Okay, so just to recap questions for vitamins. What are the fat-soluble vitamins? Go ahead. Yeah, Tara. Yes, okay. So what are the common steps in extracting fat-soluble vitamins? Ben? Before solvent extraction. Yes? Saponification, because you want to get rid of triglycerides, so you saponify them, they become soluble, the free fatty acids become soluble, and then you extract the vitamin, which is non-soluble yet, with solvent extraction. What are some precautions during sample preparation and why? Okay, Ben? So avoid oxygen presence because some of the vitamins can oxidize. Can you name one that can oxidize? You did in the lab today? Vitamin C. Jesse, you had your hand up. Did you? No? Okay. What other than oxygen? Yes? What's that? Yes, chelating agent because again in vitamin C some presence of metals such as iron or copper can enhance oxidation. Agnes, what did you want to say? Light. Can you name a vitamin that is susceptible to light? Huh? Vitamin A. Claire? Riboflavin. Josie? Temperature, of course, there are thermolabile vitamins. Vitamin C again is one.
And pH?
Then pH, yes. Some are pH sensitive, so we have to be careful with not having high pH, especially again for vitamin C. And also heat and alkaline condition for thiamine is also will cause degradation. All right, so using not Monday group, using the endophenol assay for vitamin C, what do we do if we want to measure the aldehydoascorbic acid that might be present in the sample? Bill?
Add a reducing agent.
Add a reducing agent. Very good, because you may have, while the sample is stored, you might have mild oxidation of vitamin C ascorbic acid to aldehydoascorbic acid, which is still viable, that means still biologically available. To make sure that we can capture all forms of vitamin C, you can add a reducing agent, and then you reduce aldehydoascorbic acid to ascorbic acid, and then you can quantify all vitamin C content. Okay, good. So the last set of vitamins that are water soluble, B1 and B2, thiamine, riboflavin. So again, you use a chemical assay. In this case, both can be measured determining fluorescence. Both are thermally stable under acidic conditions, and they are water soluble. So you use acid solution and you autoclave around 120, 130 degrees C to extract them in the water. For thiamine, since they can form phosphate esters, you add an enzymatic step to remove the ester, the esterification, and then you do chromatography step just to clean up, to remove any interfering substances that may fluoresce. You don't want that. And then you oxidize thiamine to thiochrome. Thiochrome is very prone to oxidation and also, not oxidation, sorry, light, I want to say. So light degradation. So once you perform the oxidation step, you want to make sure that the reaction is carried out under subdued light. And then the thiochrome can be measured, you measure the fluorescence of that. There's the excitation and the emission wavelength. For riboflavin, same way, you extract with heat under acidic conditions, and again you perform under subdued light because it's sensitive to UV light. and then you oxidize any interfering substances that might interfere with the absorbance and fluorescence measurement. And then you measure fluorescence. Again, there's the excitation and the emission wavelength. So detailed procedures are in your book, but you're not required really to know the detail of the procedure as long as you know the general procedure. Okay, so that's vitamin. End of that. This is what you're going to do in the lab. We already talked about this. So we will continue for a little bit on minerals. Okay, mineral analysis. Let's list a few reasons for why it's important to determine minerals. Michelle? Huh? Health claims, yes. You want to determine the nutritive or the required daily intake of those. For a nutrition label is one of them. Bioavailability, yes, for nutritional studies, yes. And if you're taking experimental nutrition next semester, some food science students do, they measure iron actually in the blood. And they can be taken up by the reaction, yes. So I'm going to expand on that, not just for shelf life, also for processing. So let's say we are producing white flour. So we're removing bran, most of the bran out from our white flour. We're losing some of valuable minerals such as zinc and iron and others. So you are required, the producers are required to add back some of the minerals lost due to bran removal. Another example of processing effect, for example, if you're producing cottage cheese, a lot of the calcium is lost from the curd due to the low pH. So you lose some of that mineral due to processing. So you want to make sure you fortify back with calcium. Let's see, what else? Salt is added as a processing aid for flavor, for shelf life, for other purposes like protein separation. So this is an health impact, and it's supposed to be labeled on nutrition label. So addition of salt can become problematic, although it is required for many different processing. Have you heard of the term? Yes? Toxicity is very important. There are some minerals that, what was the most recent outbreak in rice? Do you remember a few years ago? You were going to say something.
Did you say in rice?
In rice, yeah. It was recent, relatively recent, 2 to 3 years ago.
Is it arsenic?
Arsenic. So arsenic is needed for the body in ultra trace amounts, but excess of inorganic arsenic acid is actually a problem. A toxin can cause cancer, diabetes, cardiovascular disease, especially the inorganic form that comes from rocks and water and pollution in general. So yes, toxic. I was going to say one other thing that is very, very commonly tested for, and some of you are including this in your projects. It's hardness of water. Because hardness of water impact different processes. So let's say you have high amount of calcium in water. This means if you're producing processed vegetables or fruits, you might impact the final structure of that fruit. By having a water that is high in hardness, high in calcium, for example, magnesium, water might be lost from the tissues of the fruits and vegetables to the outside of the water. And water is used a lot during processing for blanching, for actual mixing, part of the formulation. what is the current nutrition label requirement and what's the new nutrition label requirement in terms of minerals? You see, I keep putting that nutrition label up there for you. Yes, Agnes? Huh? Iron and what was the first one? Potassium. So now addition is potassium. Before potassium there were 2, 3, how many minerals?
Well, there's calcium, vitamin C,
Minerals, only minerals.
calcium and iron.
Calcium and iron down here. What's up here? Your sodium. So you had sodium, calcium, and iron, and now the new one is still sodium is up there, calcium and iron is still there, and potassium is added. So now these are, so 3 and now there are 4 minerals that are important. So it's important to determine elements because of the, of course, body requirements. They have the macro elements that are required are at 100 milligrams or greater per day. They're called macro elements. Trace elements in milligrams, few milligrams to micrograms per day. And of course, there are some toxic elements. Arsenic is one. It's needed, like I said, arsenic is double that element that you needed in very, very small, even less than trace, but high levels can be toxic. So among the toxic you have lead, mercury, cadmium, and aluminum. Okay, so there are different ways of determining different elements in food. We've already gone through atomic absorption and ICP, which a lot of minerals, especially the metallic form of the minerals, can be quantified using AA or ICP. And they're often used when you have really large amount of samples that you want to analyze. But when you have few samples and select minerals, there are other methods that are traditional methods and they are still used to date. So you have the titration methods. We're going to talk about hard water and also salt titration methods. There is the colorimetric method. The common one is for phosphorus. It's a very common method to determine phosphorus. And then the ion selective electrode, where you can detect, like you have a pH meter, but instead of electrode for a hydrogen ion, it would be electrode for a specific ion. With, like anything, like any analysis, you have considerations. So some element determination require that you do a pre-ashing step where you get rid of all organic matter and you dissolve the ash, resolubilize the ash in acid. Others do not require a pre-ashing step. Some of the methods, the titration method that we're going to talk about, does not really require ashing. And in most cases where you need AA or colorimetric acid or ion selective electrode, you need to pre-ash in most cases. What precautions we need to take while preparing samples? Very important precaution for minerals. Yes, Bailey. That is true. If we're doing AA or ICP and we require ashing, yes, volatilization. Other than that, it's another important characteristic that we want to be careful. Contamination. It's very important. So we want to avoid any contamination if we are attempting to determine, let's say, iron content. You have to avoid grinding in a metal grinder. And we always run a blank for that. Interferences. Oftentimes you require certain pH, otherwise you don't get the ionization that you need for a particular titration method. You want to make sure you have the right temperature. Sample matrix, if you have magnesium in there and you're after determining calcium, you might have interference in that titration. And and the choice of reagents. So oftentimes to to have a counter effect to whatever the sample matrix is, you use what we described in spectroscopy chapter when we talked about standard addition method, where you use the sample and you spike the sample with known concentrations of your standards. So oftentimes when you're determining minerals, you follow the standard addition because you can never prepare a reagent blank that contains every other interfering component from your sample. Okay. EDTA complexometric titration, which many of you might already know this because of your project, you're determining hardness of water. This is a very common titration. And oftentimes, if you're just looking at it from a qualitative perspective, you use test strips. They call AquaCheck test strips, and they are based on the same principle as the titration method. So basically, it's based on utilizing EDTA, which is a chelating agent, and it forms a stable complex with calcium or magnesium. And you use in the titration an indicator. In this case, it's very common to use Kalmagite indicator, and once it binds to a metal, it changes color. So when it's not bound to any calcium or magnesium, it's blue. Once it binds to a metal, it becomes pink. So the principle of the reaction is to select an indicator that has less affinity to the ion than EDTA, because you have your sample and you have your indicator, and the indicator binds to your calcium or magnesium. Then what happens, you're titrating with EDTA, you want the affinity to be more to the EDTA than the indicator. So when you're titrating, the calcium will be picked up by the EDTA and will leave the indicator. When all the calcium has bound to EDTA, the next drop of EDTA taking all of the calcium will turn the indicator back to blue. So here's an example of pH is important because you want to make sure that the chelating agent had their sites to interact with the metal or the element. So if the pH is low, EDTA becomes protonated. So that means it captures the hydrogen ions and it's no longer available to interact with the calcium or magnesium. So you want to make sure that you have pH between 10 and 11. That's enough to make sure that the EDTA is available to capture calcium or magnesium. And it's a titration, obviously, like I said, once the EDTA captures all the calcium, then your indicator turns back to blue. And the strips function the same way. They are impregnated with magnesium and EDTA, and then when you dip them in the solution, you have the EDTA pick up the calcium, and then the indicator changes color. Another titration method is the Moore titration. It's a very common method for salt determination. So it's very simple and straightforward. The chloride from salt is titrated with silver nitrate. So you have the chloride from the salt and you have the silver from silver nitrate. They react until all chloride is complex as silver chloride. And then the next drop from your silver nitrate in the presence of an indicator, chromate indicator, you'll end up with an orange precipitate. And that would be the end of your reaction. And here, the moles at equilibrium, moles of silver would be equal to the moles of chloride in the sample. The Volar titration is another titration for salt, but it's a backward titration. And someone would say, if you have a forward titration, why do you need a backward titration? I don't know. It's a method that's been developed that way. But I would always prefer a forward titration, but some people go with the backward titration. In this case, you don't titrate with silver nitrate, you just add excess to your sample. You will just put in excess silver nitrate and you get the complex. Any remaining, because you had excess at the beginning, any remaining silver nitrate will react with thiocyanate reagent, and that would be what you titrate with in this case. And you would have iron as an indicator. So the last drop of the thiocyanate would, when the presence of iron, would turn red. And then again, it's a molar equivalence. Well, in this case, you take the excess and you subtract from the original, the remaining from the original, and then you get the amount of salt that was there. So you will have the total when you have a blank, and then you will have the remaining when you have a sample, and you subtract, and then you would get how much silver reacted with the chloride. And this is present also as a Quantab test strip, so same principle. This is based on the more titration, actually the forward titration. It's rapid, it's AOAC approved, it's more or less accurate with 10% relative error, and it's meant for a certain concentration of salt. Okay, with that, I'll stop here and start on that next time.